Hey everyone, this is Ashwin here. In this video, we're going to see how we can create a model for road lane detection. So in this, we are going to use TuSimple Dataset, which is a popular dataset for lane detection. We have a original image and we have a mask image, and we have to predict the road lanes accordingly. So this is basically a image segmentation problem. We already seen image segmentation problem in a different way, where we are predicting pits from the image, but this is something different. So this application is mainly used for like self-driving cars and mostly in that area, as we are detecting road lanes from the input images. So as you can see some input image here, and the road lanes, which is like a line. We can dig deep into the dataset when we are doing the coding part. So in total, we have around 6,400 images, and which is a resolution of 720 pixel, and they have split it for training, validation, and testing. So this is the data set. As you can see, there are train and test data, and they have the labels in a JSON file. We have to convert this JSON file into a mask images, so that we can consume it for image segmentation task. So in the clips, we have multiple clips. Each video is segmented by like 20 frames. So if you go into like single folder, we have like 20 frame. From each folder, we will just take the 20th image alone, because all of them, if we take it, means it will be like duplicates. We don't want to do that. So 100 is like a video file name, and 002040 is like a number of images that is present. We can combine this and this first 3 digits for creating the images and the mask files. We will see this in detail. For this image segmentation, I'm going to use VGG plus UNet. So VGG-UNet, which is a popular architecture you can see in image segmentation. You can also use UNet, but this VGG-UNet is like producing better results compared to the vanilla UNet model. So let's start the coding. So if you click on this, you can create a new notebook. So when you do this, it will automatically import that dataset which we saw earlier. So open this, and here we have to set the GPU, but we will set it later because we have to do a lot of coding, and I don't want to use GPU hours for this. So once we completed most of the coding part, we will use the GPU for training. And make sure to turn on the internet to download the weights of the model. And currently we don't have any, and here we have the dataset, so we will use this for processing. And we'll change the file name, road lane detection VGG-UNet TuSimple Dataset. Okay, now let's delete this, and we will create some code cells. Then let's import the modules, as that is the first main step for this. Import modules. Maybe let's increase the size a little bit so that you can see the code clearly. So that is clear now. Let's import all the basic modules. So import pandas as PD. Okay, it automatically started the session because of running this cell. Okay, and NumPy. These are pretty basic modules. Import OS, import matplotlib dot pyplot as plot, import cv2, import random, and import shutil for copying the files, and from tqdm.auto import tqdm. And what else is there? We have to import TensorFlow. So for this entire tutorial, I'm going to use TensorFlow. So tf from TensorFlow dot keras dot preprocessing. I think maybe we will import the image generator later when we need it. So whenever we need some modules, we will import it then and there, and later we can move all the imports at the top of the file. I think that's it for now. Let's run this. We could also add like warnings, import warnings dot filter warnings, ignore, rerun this. Okay, now we have imported, then we will load the dataset. Now for this, I'm going to create like separate working folder which I will be creating here. So I will create image folder as like a constant. That's why I'm using full caps. So TuSimple underscore processed slash images, and we will create the same for mask folder. So TuSimple underscore processed slash mask or masks. Okay, let's run this, and we have to create these image folder and mask folder if it's not present. So def create directories if not exist. Okay, path if not os dot path dot exists path, then os dot make dirs of path. Maybe I will have it as directory path, or else they will pass like file names. It will not work. So directory path and print. We will say directory created colon directory path, else print directory already exists, and again we will pass the dir path. Okay, this is done. Let's run this, and here I will call the function with the corresponding image folder and mask folder. So create directories. I'm not sure what happened to Kaggle. Recently it's not like suggesting anything correctly, so we have to type the entire syntax by ourselves, which is pretty inconvenient. So again we will call it with the mask folder. Okay, run this. Okay, we have created the directory. Let's check. So whenever we create some directory, it should be present in the Kaggle working. So here we can see the directories, and inside it we have to move the images, which we are going to do it now. Okay, first step, we'll again create a markdown, move images to the image directory. Okay, you can also copy it, so it's not a problem. So I will copy it, or else if we want to reuse the data set, means it will be difficult. So we will copy the clips path. So clips path equals, which is the data set, So here if you go down in the train set, we just need this clips path. So paste this, and from here iterate through each directory. Okay, for clip directory in os dot lister of clips path, clips path. Okay, then I think again if we use clips path it will be difficult, so I will use clips dir path and os dot path dot join clips path comma clip dir. Okay, so this will combine these path and we will get this. Again we have to do another iteration. We will just print the status at least. So processing clip, and we will display the clip directory just to see which folder is getting processing right now, and then iterate through each subdirectory which is inside this. So for frame directory in os dot list directory of clips clip dir path. Okay, again we have to get the complete frame path which is the same as above. So os dot path dot join of clip directory path and frame directory. Okay, and from here, as we already discussed, it will have like 20 frames, and we just take this 20th frame if we have. So 20 dot jpg, then check whether the frame exists, otherwise we don't need to add the path. So if not, os dot path dot is file of frame path, then continue. If the file is present, I will add a comment for better understanding. Check if file is present. So if it's not present means we will just continue to the next directory. Then create new file name based on last two directory names. So what I'm going to do is, from the whole path I'm going to take out like around like 7 characters from it and combine these as a image path. So I will just show you. So temp equals frame path minus 7. We are just removing 7 characters, and dot split of slash. Then I will just take the last two directory. So -2 colon, then new file name, format of okay. So here temp of 0, temp of 1. I think we will use temp here, it's better. And then we will have new file path. New file path equals os dot path dot join of image folder which we had at the top, image folder, and inside the image folder I will have the new file name. Okay, then copy the file. I will show you how the process works just after this command. So sh.copy from the frame path to new file path. Okay, this whole function is done. So the frame path will look like this. So frame path will look like this. So I will take the 20th frame here, copy and paste. So here you can see I'm just taking out last 7 characters. So 1 2 3 4 5 6 7, and we will take this alone. Okay, and then I'm just concatenating these two. So this and this, as I'm splitting the last two, taking the last two directory and having it in the path. So once it's processed, I will show how the image file names look like. So we will close this and run this one. So it's processing clip by clip. So we have like 4 folders inside it. So it's processing it one by one. Let me close this and open this images. It'll take some time. So now you can clearly see it, right? So this is the clip folder name, and I added the underscore and the last folder name. So that's how it works. I think we could also use some better optimized way to take the last two directories, but this also works. So I think the process will be done soon. Then we will print the total number of images, in dataset for the training. So len of os dot lister of image folder. Run this. So we have 3626 images, which is pretty good number of images for image segmentation. Then we have to do the same for creating the masks, but we have to do additional processing here. So copy images to the image directory, create mask for the images. Okay, now we have to read these 3 label data. So I will have df1 equals, maybe before that load the dataset JSON files, load pd dot read JSON of. I just have to copy the path, so I will copy it directly here, and we have to repeat the same process for df2 and df3. Okay, and copy the path, paste it here. Okay, we have covered 3 JSONs. We will concatenate to a single data frame for easier processing. Combine into single data frame. Concat of a list df1, df2 and df3. Okay, then df dot head. Let's run this. So we'll just see the lines. Okay, this should have like additional parameter. Here we have to pass. lines equals true, and we will do the same, and let's run this. Okay, so these are the mask data, but it will be in terms of pixel values. We have to concatenate these pixel values to draw the line ourselves. So this is the image, and for the corresponding image we have the height pixel and the lane pixel. We will have like 2 lanes or 4 lanes, like we will have 2 lines or 4 lines in the mask. So we will see the mask after creating and visualize that. So we have to process these files. We will create another function, create function for generating mask, def generate lane mask of row. We will pass each row and process it. Then I think that should be enough. If we need anything, we will add it later. Create a mask of all zeros. So if we create an image with complete zero, means it will be like a black image, like the complete image will be having black color. So mask equals np dot zeros of 720 comma 1280. As we already know, this is the resolution which we had before, like we saw in the dataset description. And d type equals np dot uint 8, and extract data from the row. So we have h samples here. So h samples equals row dot h samples, and then lanes. Totally, as I said, it might have different number of lanes. Totally at max we have like 4 lanes. So row dot lanes. For this dataset, I think we have to like do this processing, but some other dataset might have the direct lane images, so you can skip these steps if you are using different dataset. And raw file equals row dot raw file. Okay, I don't think we will need the raw file. Maybe at least for getting this file names, I think it will be used. Okay, now create mask. Lane will be having 1, which is white color, and non-lane will have 0, which is the black color. For lane in lanes, so this is the lanes. -2 means that means there is no point available, so we have to process it accordingly. And the head samples will remain the same. So exclude -2 data points, and then head samples filtered equals for x comma y. We are processing the head samples here in zip of lane comma head samples if x not equals -2, then we will take y. So what we are doing is we are iterating this list and this first list, and whenever there is -2, we will ignore these point. So we will ignore first 4 points here, and whenever we have some value other than -2, we will take these points. So that's why h samples filter. So this is first step. We have to do the same for lane filtered equals, again, for x in lane, if x not equal to -2. Okay, now it's done. We have to create a array of points, create array of lane points. So using these points we will connect it to form a line. So I will create the lane points from this np dot array of list of zip of lane filtered and h samples filtered. Okay, then we will use OpenCV to update these lane points. That means we will draw a polylines. So update lane mask here, cv2 dot polylines of the mask which we created before this mask, and we will have the lane points. Lane points is closed equals false. Color will be white. So 255, 255 and 255. Then thickness, I will use it as 15. You can set the thickness accordingly. So next, generate mask file name. So here also we are going to use the same format which we done before. So temp raw file which we had earlier, which is the raw file path. I will just remove the last 7 characters and split it by slash, then take last 2 directories. Then we have to create mask file name equals f underscore, sorry, this will be outside, and again we will have JPEG. So temp of 0, then temp of 1. So this will be the mask file name. Then mask file name path equals os dot path dot join of mask folder and mask file name. Then write the image, write the mask image, cv2 dot IAM-write of. We have the mask and mask file path, mask file name path comma mask. So this mask is updated with polylines, and we are writing it to the new path which is mask file name path. Okay, let's run this. Okay, now generate mask for index comma row in tqdm of df dot iter rows and total equals, just to keep track of the progress we need this, so length of df. Then generate, okay, it's not even suggesting anything, so generate lane mask of row. So whenever you are running the whole loop, it's better to make sure to test it with a single sample. So let's run it once. Ideally it should have at least a single image. Okay, I could not load it, but it has like 52 kilobytes. I think this is good. Let's run the whole batch. Okay, this is quicker. So we will again display it for the mask. We know it has 3626, but still we will make sure it has all the files. So mask folder. Okay, we have all the images that we need. Next, we have to visualize the road lanes along with the images. Data visualization. I know this is taking very long, but all these are necessary to clearly understand the problem. So def visualize image name. So first I will get image path from this. So get paths. So image paths equals os dot path dot join of image folder and image name. Then mask path. It's the same. We have to change this folder to mask folder. Then we will read the image and mask. So image equals cv2 dot imRead of image path. Then image equals cv2 dot convert color of image cv2 dot. So when we read, it will be in BGR format, so that's why we are changing back it to RGB. So BGR to RGB. Then mask, it will be a grayscale image, so cv2 dot imRead mask path. Okay, now plot the image. Plot dot figure fig size. I will have 20,8. Then we have to display both the road image and the ground truth. So plot dot subplot of 1, 2, and we will plot the first index. Plot dot imShow of image. We will normalize it by 255. And then plot dot title. I don't think it's needed now. We will check it. And road image. Then we have to do the same for mask. Plot dot subplot of 1, 2, 2. Plot dot imShow mask cmap equals gray. Otherwise it will give some different color, so it's better to pass the color map. And title will be ground truth mask. Okay, that's it. Then show the images. So plot dot show. Okay, now that is done. Let's take a random image from the list of images we have. So I will use random dot choice of os dot list directory of image folder. and then once I got the image name, I will call the function visualize image name. Okay, image name. Plot is not defined. Did I miss the import? Okay. Let's run this again. Okay, now you can see it, right? So this is the lanes 1, 2, 3 and fourth lane. So some lanes have car as well. It's overlapping, but our model should identify the lanes and automatically correct this. So this is the ground truth. Let's also display it for a couple of times to see different images. So this is also have like 4 lanes. So this is like somewhat very clear. Let's try a different one. Okay, now you can see this have only like 3 lines. So that's why the list or array in lanes which we processed before, it might have 2 lanes, 3 lanes or 4 lanes. So based on it, we have to do the prediction. So this is clear. So this is the data visualization. We know what is the input and what is the output. If you don't want this, you can switch off the axis, but for now it is fine. Let's display maybe 2 more. This is more similar. I'm just expecting some curves like this, but okay, so this is somewhat different. So everything is like a video. So from the video, they are just process those clips. So that's why most of them are like somewhat similar. So this is fine. And then we have to process data for training and testing. Process data for training and testing. So let's create like new folders for training and testing, which contains both images and masks. So train image folder equals TuSimple processed slash train slash images, then train mask folder or test image folder. So TuSimple is the same, so I'll just copy paste. This is test, and we will have train mask folder. So here we have train masks and test mask folder. I'll just type it out. Processed test and mask. Okay, we have to create this folders. Let's run this. We already created a function, so we will reuse that function now. So for folder path in a list of train image folder, test image folder, train mask folder, test mask folder. Create directories if not exists. Folder path. Run this. Okay, so the dataset is created. Let's refresh this folder. Now you can see train and test, and inside train we have images and mask. Okay, this is good. Then we will get the list of images and mask and split it into training and testing. So for that we have to import a function. So from scikit-learn dot model selection import train test split, and I will have images names and mask names. Okay, here for file in os dot list directory of images folder, I think image folder, if file dot ends with .jpg. Sometimes if you are running it in Mac, it usually creates some DS store, so that's why we have to check this, and we have to do the same for mask, but in this case we will have mask folder. Okay, and split for train and test, train images, test images equals train test split of images comma test size of 0.1. If you have more images, you can have a broader test set, and random state equals 42. So this will just split the images for training and testing, and later using this we will just move the corresponding files to the new folders. So run this, and we will just display the length of train images, len of test images, so you can see the split. Then move files to the corresponding folders. For file in train images, so it has only the name of the image, so it's easy for us. Move the image and mask. We have to do the same for test images as well. So sh-util.move of os.path.join. Maybe I'll have source equals, because sometimes doing everything in a single line makes it very messy, even it's like a optimized thing. So image folder, from the image folder, and I will have the file which is the image, and destination will be the same, but here we will have train image folder. So we have source and destination. Now we have to repeat the same for mask. So here it will be mask folder, and here also train mask folder. Okay, now these two will move the files, and we have to do the same for test images, test, and this is also a test. Okay, so this will move all the files to the corresponding directory. Let me just double check whether everything is present in the correct manner. So I think everything is correct. Let's move this. Okay, for confirmation, let us just open the image. Okay, nothing present in the image folder. Let's open test because it will have less number of images. So here you can see 10120, and we will check the same for mask. Okay, all the files are present. Now we are good to go, and we will jump into feature engineering. So we have to get the image and mask using a function. So feature engineering, or you could also say data transformation. Now def load image of image path comma mask path image equals tf dot io dot read file of image path, then image equals tf dot image dot decode jpeg image comma channels equals 3 because it's a RGB, and for mask it will be like 1. So image equals tf dot image dot resize. We cannot pass the 720 pixel resolution image to the model because otherwise the training time would be very long. So I will pass the resolution as 224, or you can also process it with 256 if you need. Then we will normalize the image. So image divided by 255 normalize to 0,1, and we have to repeat the same process. So mask equals tf dot io dot read file mask path, and I'm just redoing the same thing, so I'll quickly do it. Here in this case it's a gray channel, like a single channel, that's why it's a grayscale image. So the channels will be 1, and this will be again the same resolution. If you change it, you will face a lot of errors. You have to have same dimensions. So in this case I will have it as size and use this variable to avoid confusion, and we have to normalize the image. It will be mask divided by 255, same as before, and then we will return image comma mask. Okay, so this is one function. Another function is we have to read the dataset from the folder we have. So def dataset from folder of image folder comma mask folder. So here image files equals sorted of a list for file name in os dot list directory of image folder. So here we are doing the same thing as above while we are like checking this. So I am basically doing the same thing here. Here we will pass the image folder, everything remains the same, and we have to do the same for mask files equals the same function, but here mask folder, then dataset equals tf dot data dot dataset from tensor slices of again image files comma mask files. Then we have to like map it. So dataset equals dataset dot map of lambda lambda image path comma mask path colon load image, which is the previous function which we defined, load image of image path comma mask path. Okay, now that is done, we will return the dataset. So run this. Okay, next we will load dataset from folder. So train dataset equals dataset from folder of train image folder and mask image folder. Okay, we have to do the same for test, so it's better to type it instead of copy paste. So dataset from folder of test image folder and mask image folder. Okay, let's run this. Mask image folder. Okay, this is train image train mask folder, train mask folder, and this is test mask folder. Okay, this is done. Then we have to do some optimization, like for faster processing. Set config. So here I will set the batch size. Batch size equals 32 and buffer size equals 1000. Then we will do the optimization. Optimize for performance improvement. Train dataset equals train dataset dot cache dot shuffle of buffer size dot repeat dot batch and batch size. This I got it from TensorFlow documentation. So most of the changes they have usually within the documentation. So make sure to check that. Maybe at this point they might have updated to more optimization techniques here. So here we will have train dataset dot prefetch of buffer size equals tf dot data dot experimental dot auto tune. Okay, and we have to do the same for test, but mostly we have to do it for train because the large portion of the images are in the train dataset. So test dataset is only used for evaluation. Still we will have test dataset dot batch of batch size and we will again do the prefetch here also. So test dataset dot prefetch buffer size equals, I just copy this. Okay, I think the syntax are correct. Let's run this. Okay, I didn't throw any error. So hopefully maybe in the training we will get to know whether it is working or not. Then we have to create another function for displaying the image during the training. So that's why we will have display sample image list plot dot figure of, we will show image, ground truth and the prediction. So that's why we need this function. So fixed size of 10 comma 10. We can change it later if we need. Then titles equals, we will have image, ground truth, and then predicted mask. We can also have like true mask to make it like rhyming. True mask. Okay, for I in range of len of image list, plot dot subplot of 1 comma len of image list and I plus 1, plot dot title. So it will just dynamically show the image. If we don't pass the predicted mask, means it will adjust it automatically. Titles of I, then plot dot im show of tf dot keras dot preprocessing dot image dot array to image. Because these are like process data set, it will be in the array format. That's why we are converting the array to the image back again. So image list of I, and plot dot axis equals off. It won't show the additional axis like before. Then plot dot show. Once all the details are filled, we will show the image. Run this. Let's test it with the train dataset. So for image comma mask in train dataset dot take of 1, I'm just taking the first batch. So here we have to, we can just directly display it. So display sample of a list image of 0. It will have the batch, so it has like 32 images, so that's why we have to do this. Mask of 0. I think that should work. No such file or directory. Okay, so this should be like a complete path. So it will be like os.path.join of image folder comma file. Okay, so this is better, and we have to do the same for mask folder. Okay, now this should be good. Let me run this. This should be image folder. I just used a global variable. Okay, let's run this again. Okay, I think now it's processing. Now you could see the image and the true mask. So this is how the result will look like. And if you want to have a grayscale image, means you have to use CMap in the IM show. But with this generic function, it is hard to find. But this is also fine for us. So our data loading is also working fine. So it's better to check like each part like this. Okay, now this is done. Let's go for model creation. Model creation, which is VGG-UNet. Okay, I think typing the whole model from scratch, it will be very difficult and it might take like a long time. So I'm going to use my model which is already created. I will also take the metrics function, so it will be easier for us. You can also take the metrics, or you can use different metrics for the models, but the main metrics would be like dice coefficient or dice loss. So let me just quickly get the code snippets. Okay, now I got the code snippets. It can accept any input shape with 3 channels. So this is the con2d relu batch norm for the UNet. Here you can see I'm just downloading the image weights, and I'm just making everything as trainable, and I'm just removing include top as false because it will remove the classification layer. And these are the first 5 layers, and from the 6th layer, as per the UNet architecture, we will combine layer 5 and layer 4, and here layer 6 and layer 3, like that we will do it again and again, and finally we will have a single dimensional output, which is in the shape of 224 cross 224 cross 1. So the final activation will be a segment. So the value of the output will be in the range of 0 to 1 as a grayscale image. So this is the model architecture, and this is the encoding step, and this is the decoding step. So let's run this. If you want a different shape, means you can just pass different shape here. So this will just download the weights of VGG, and rest of the layers we will train it using the data samples. And these are some of the metrics. So we cannot use like built-in functions for the image segmentation. So we have to like flatten the values, because we are processing the image, right? So it will be in a 2D matrix. So we have to flatten it, make it like a single dimensional list, and then we will compute the calculation. So here dice coefficient is very important, because using this only we are calculating the loss function for our model. And we also have precision and recall, both having the same idea. So we will just flatten the outputs and calculate it. And we also have the accuracy value. Let's run this as well. Okay, now we will compile the model. Compile the model dot compile of optimizer equals Adam. You can also use the SGD, but you have to set some additional parameters here. Already this code is like very long, as you already see. That's why I had to like copy some of the snippets to save some time. And we are using dice loss for this. Other than that, I think they might use binary cross entropy, as the values will be in the range of 0 to 1. And metrics, I will use all the metrics that we have defined. So dice coefficient. What other things are there? Recall smooth, precision smooth. So precision smooth, recall smooth. I will close this. Accuracy. Then I will also print the number of parameters. That is present in the model. So model dot count params. Okay, I think I missed a C. Okay, now this is done. Let's plot the model. We have to visualize like how the model is structured. So tf dot keras utils plot model. You can also like save the image if you need. So pass the model, show shapes equals true, expand nested equals false, and DPI equals 64. It's like pixel intensity. If you run this, so this is how the model will look like. If you scroll it, all these layers are like connected with the decoder layer for better performance. And finally we are getting this output. So it's better to like visualize the model. If somewhere the calculation doesn't make sense and you are getting some error means, so you can easily debug it and fix it. So that's how I debug the model architecture based on this input shape and output shape. Okay, next we have to create few more functions. Create mask from prediction. So def create mask. You can ask, we are already predicting the mask from the model, but the prediction value will be in the range of 0 to 1. Whenever there is some mask value, we have to like round it off to 1, because then only we can have the full clear line, or else some shaded regions will be there. So pred mask equals tf dot math dot round off prediction mask round to closest. Okay, and then we will return prediction mask. So this is done. So then we will create show predictions. Here we will have a dataset, and dataset none. I will have it as sample equals none, and number of predictions I will have it as 1 by default. So either I can pass the test dataset for doing the prediction, or I can pass any image sample for prediction. So this function will be useful. So if dataset is present means we have to do the same like before. So for image comma mask in dataset dot take of num. So based on number of predictions that we need, we will do it. So prediction mask equals model dot predict of image. Actually this is images and mask. It will take like 32 it will have like 32 images because of the batch size. Then we have display sample function which we had before. So from that I will pass image of 0, sorry, images of 0, then mask of 0. Finally we will pass the prediction mask, which we have to pass it to create mask. We will do it before itself. Pred mask equals create mask of pred mask of 0. Again it will have 32. We are just taking like a first sample out of it, and here we will just pass the prediction mask. Else we might only have a sample. We have to do the prediction and do the same thing here. So what we will do is, so in this case we won't have a ground truth. Maybe we could have like a separate function where we could get the image and plot it. So I'll just have this function only for the dataset. Okay, let's run this, and some issue here. I didn't close it. Okay, now this is good. Then show predictions of trained dataset. By default I will just have 1. Currently the model is not trained. We will just see whether the function is working correctly or not. So it's taking some time because it's processing in the CPU. So that's why. In the meantime, we will create few more functions. Here you can see it just extracted few images and try to do the segmentation. At least with the predicted mask we could see some things are happening because it extracted some features. So let's set callbacks and logs. Callbacks and logs. After each epoch, we will try to set it like you have to do a prediction and show the sample. So it will be easy for us to keep track like how the training is progressing. Otherwise, we have to test it at the end, so, which is pretty inconvenient. So from TensorFlow dot keras import callbacks and import datetime class display callback of callbacks dot callback. I'm just overriding the existing function. So def on epoch end self epoch logs equals none. Then we will do the show prediction. Show predictions of test data set, and again I just need only one sample. Then print sample prediction after epoch. I will have the format. Okay, then I will have a new line just to separate this. This is good, and we will have log directory os.path.join of logs date time dot now dot string format time of, we have to pass the format which we need. So year, month, day hyphen hour, minute and second. Okay, now log directory is created. Then we will define the complete callback in a list. So display callback, which is the function we defined above. Then callbacks dot tensor board. If you want to track the progress, we can use this log directory to track it. Histogram frequency equals -1. Then so logs are done. Then callbacks dot early stopping. This is also important. If the validation loss didn't increase for, let's say, maybe 5 epochs, I will stop the training. So verbose equals 1, and again callbacks dot model checkpoint. We have to store the best model checkpoint from the training for reusability. Best model keras verbose equals 1, save best only equals true. Okay, now the callbacks is created. Now we can train the model. Let's do the last setup. Epochs equals 10. As this is a testing, I'm just going for 10 epochs only. Steps per epoch len of os dot list dir of train image folder divided by batch size, and validation steps the same part equals, I'll just copy the same. Here it will be test. Okay, now here we will train the model. Before that, we have to change this accelerator. I will use P100. So this will just restart the session, and I will complete the remaining. History equals model dot fit of train dataset. Train dataset epochs equals epochs. I will just have it in new line, otherwise we cannot see everything. So epochs, I will pass this as well. Train data validation data equals test dataset. Okay, then steps per epoch, steps per epoch equals steps per epoch. What else is there? Validation steps, and finally callbacks. Okay, everything is done, and we have to start it again. Let me just check whether all the data is present. Okay, we can skip some steps here, so let us quickly do it. All these processing are done. So okay, now only the session is started. Okay, mask images, data visualization remains the same. Train image folder, and these processing should happen. Okay, from here I will start it here, and this. Okay, I think images, I think it's better to start it from scratch itself. I think some parts are missing. So it's just processing the files one by one. Data visualization we can skip. We'll just see if the processing is done or not. Okay, this is almost going to be done. Even for you, it's better to do like this, because don't waste the GPU resources. We have like 30 hours only, so it's better to do like this. Okay, all these are done, and let's do the feature engineering. Let's display a single sample. Okay, it's working, and model parameters printed, create mask, show predictions. Now this will be like much quicker, because we are utilizing GPU now. And then we will do the callback, and finally validation steps. Okay, I added an S here. Okay, let's remove this. First data will always be our train dataset. So let's steps per epoch. Okay, I think the training has started. The GPU memory is around like 8.5 gigs. If you have a bigger GPU, you can increase the batch size, but I would suggest to keep the same. So now it started the processing. As you can see, CPU is 100 and GPU is also 100. With those optimizations, I think it will parallelly do the prefetching and cache the data, so the GPU can train the model very quickly. Okay, now you can see the train loss and accuracy. Over the time, this will improve, and we can also see some validation results from it. So let's wait for the epoch to be complete. I think we set it around like 10 epochs. So after that, we have to plot the model accuracy or dice coefficient along with the loss. So I will have plot the metrics for the 10 epochs at least. You can see it is started learning. Let me just create some code cells. Now plot train and val loss accuracy. Then we will plot the loss. Plot dot figure fixed size 12,4. Then plot dot subplot of 1, 2 and 1. So the first plot will be on accuracy. Plot dot plot history comma history. Okay, wait, history dot history of accuracy. Then the same here we will plot validation accuracy. So val accuracy. Then plot dot title of I will just have it as accuracy. Then plot dot x label epoch. Then plot dot y label accuracy. Then plot dot legend train test location upper left. I think it is not needed. Otherwise it will show it on the right, I guess. So we will see. So we will do the same for plot train and val loss. Okay, now here accuracy will be replaced by loss. Okay, this is done. And finally we will plot the graph. So plot dot tight layout and plot dot show. Okay, let's see. Okay, we are seeing some good improvement actually. So this is the starting prediction after doing like single epoch. Over the time you can see it's getting the hang of it. So in 3 epochs itself, it's learning the features very well. I think it's mostly due to the pre-trained model from the VGG. Other than that, we do have like significant number of samples to learn the features automatically. Okay, once we have plotted the metrics, we will do some test predictions from the test data set. So test predictions show predictions of test dataset comma 10. So it will display like 10 images from each one of the batches. Then we will also have one more snippet test from image path. So from the path we will try to get the results. So what we will do is image path equals, for this we need an image path. What I'm going to do is I'm going to take some images from here. So I think this will be static. So I will take this 20th image for our example purpose. Okay, so this is the image path. Then we have to process this like previously. I think many people have asked the same thing, so that's why I'm redoing this part. So this is the process image. I'll just copy this and paste a function here, and I will call this as load test image. I don't want to override the existing function, so that's why. And here I will return image. So image equals load test image of image path. So this is a single image. After that we will get the prediction mask. Prediction mask equals this, and we will get the prediction mask from the model. So model dot predict of image. I will pass it in the list because it will have like a multi-dimensional, as we are training it with like batch size, right? As we are training it with batch size, right? So that's why I'm passing it as like this. Otherwise you can also reshape the image to have like the additional one dimension. After getting the prediction mask, again we have to process it using the create mask function. So equals create mask of prediction mask of 0. This will return a list with contains like a single mask, and we will get the prediction mask out of it. Then we could plot it like before. I think I already defined a function somewhere. So that display sample function, we could reuse it. Okay, so this is the function. So here we are passing the image and the mask, but the titles are different, so that's why we have to create like another function here. Display test sample. I will have only two titles, and from here I will have display test sample of image, and then the prediction mask. Ideally this should plot the image, like the input image and the prediction mask. I think still the training is going. Okay, we are reaching around 9th epoch. Let's wait for this to complete. Okay, I think the training is done. So you could see that the validation laws keep on improving, and we are saving it to the best model.keras, and if it's not improving means we will just leave it as it is. And you can see the validation training accuracy and validation accuracy, but we have to focus on like dice coefficient, as this is more important. And you can see the progression. I'll just go from the first epoch. You can see how the model learns and progresses it. After like 6th epoch, the alignment is much better. You can train it for more epochs if you have like more samples, or you could push it until like 20 epochs, maybe 20 or 30, and see how much you can train without overfitting. So once this is done, let's plot the graphs. Okay, I have to use 2. So the accuracy and loss is steady. It's not like oscillating that much, and we are getting like a good accuracy here. And we can load the model again, load the best model. So here I will have like a new model. If I lose the old model, that will be difficult. So that's why I'm just having it as like a separate variable. So tf dot, or I will just have it as best model. Best model equals tf dot keras dot models dot load model. The path best model dot keras, and I will also show you where it is. If you close this in the Kaggle working directory, you can see the best model.keras. You can also download this model if you want to reuse it, and you can see the logs here. You can use these logs for displaying it in the tensor board. And best model.summary. Okay, you have to pass the function names as well, because those are like custom functions. So I will just have the same for the best model as well. I think even here you could pass the functions. So let's run this. Okay, instead of compiling, what I am going to do is I will just use this directly as custom objects equals. You have to pass the name. So here it mentioned the names, right? Dice loss, all the things. You have to pass it here. So dice loss. Make sure to define the functions from before. Okay, now dice coefficient, as it's the same name, it is fine. I will load this in a new line because it's not clear. Okay, now precision smooth, recall smooth, lastly accuracy. Let's run this. Okay, now it is working. As you can see the whole summary of the model here. We can remove this line, and I'll just comment this as well. Maybe you can update this function to show, like, to use the best model. So for now I'll just run the predictions. So here you can see it is equal to the true mask, whatever the mask which is predicted. As I said, I just trained it for like 10 epochs. For 10 epochs, these results are very good. If you can train it for 20 or 30 epochs, that would be much better. And we will try this one. So here I will use the best model. Let's try. Okay, here we have to do like few more changes. So this image with the list is, it's not like working. So we have to like expand the dimensions. So I will have test image tf dot expand dims of image axis equals 0. We will pass that test image here. Then this will be a list. So let's run this. Okay, so this is the new image. If you have a new image, you can just pass the path here and you can get the prediction like this. So this is a complete tutorial from end to end training and testing with real image. Everything is completed here. I will just have it as real image here using a VGG-UNet model. So I think this application will be very helpful if you are like into self-driving cars and robotics, etc., because they usually use some counter detection and do basic processing there. But using this model, I think you can predict the road lanes accurately and steer the vehicle in the correct manner. And that's pretty much it, guys. We have done a lot of work in this video. If you are following the video from end to end, I think you will have a better understanding on how to do this image segmentation end to end. And if you like this video, hit the like button and don't forget to subscribe the channel for more videos like this. See you guys in the next video.